All right, everybody can hear me?
Yes, sir.
All right. Oh, here, a quick pitch. A buddy of mine is moving and he's looking for a couple people to help him load a truck on Saturday afternoon in Mequon. So if you're looking to make some extra money, message me and I can get you in touch with him. So catch me on Slack or email or whatever. All right. Let me get the... What class is this? 470? All right, good. Let me share this screen. Actually, I'm going to share. What am I going to share? I'm lost. Okay. And as usual, if you have questions or anything, just shout out. For starters, our classroom. We're actually missing. Oh, hold on. I gotta admit somebody. I hate this thing where you have to admit people into the class. Okay. For starters, the room we're scheduled in does have a COVID capacity, I think, of like 12 or 13. I don't remember what the exact number is. So we technically would all fit in the class. So I think that we're fine. I still, am open to, if I'm doing this for all my classes and I put it in the email that I had sent. If you would prefer to attend online, that's fine. So every class I'll be doing it in this exact same format. So I'll start up a Zoom session. I'll record using Zoom. So I might have people sitting in front of me in the classroom. I might have some people attending online. I guess it's possible. There's might be some people who can't make it and who go and watch the video later that day, because I'll also record every lecture and put it up on YouTube. I'll put a link to the playlist up there. So lots of different ways of getting the class. I don't care which of those ways you take advantage of, as long as you don't end up using it as a crutch. So don't say, well, I want online because it saves me a 40-minute commute. But then say, well, I don't learn very well online. You have the opportunity to come face to face. So either make the drive or, if you want to do it online, that's fine. It doesn't matter to me. All right. So questions about that? Okie dokie. And then let's see, the book for our class is called Essentials of Programming Languages. It's this book right here. You can probably, it's 3rd edition. You can probably find it online relatively inexpensively, maybe used or something. There is a PDF of it floating around, which you should absolutely not use, but it is the identical book to what we're using in class. Okay, so normal breakdown for grades. Bible homework, 10% of your grade. All those assignments are already up. We're doing the book of Acts this semester. So it's 2 chapters per week, due by midnight on Friday. All the assignments are already under the content section under Bible homework. So, you can certainly knock all those out right away if you wanted to, but you certainly don't have to. My encouragement would be do it on a week-to-week basis. That way you get into the habit of reading the Bible. But if that is going to be contradictory to your study habits or whatever, just make sure you don't turn them in late. I won't accept them late. So that should be a free 10% of your grade right there. Assignments, 50% of your grade. Same as we've done in the past, where if you want to work in groups and things like that, I don't care. I'm not going to be looking for plagiarism or anything like that. But at the same time, I will find out in the midterm and final whether or not you're learning this stuff. My usual policy, where final exam, if you do better on it than the midterm, I'll replace your midterm exam grade with the final exam grade. So you have every opportunity to succeed in the class. All right. So questions about the overall class thingy grading scale stuff? Okie dokie. So remind me, what's a programming language? What's the job of a programming language?
It's a bridge from English to, I guess, like the computer language binary, the solving problems.
I like that word, bridge. It is a bridge. I really like that word, actually. Yes, so it is a bridge between a human language, natural languages, and something that the computer understands. So it's a translation tool, right? The idea is that human beings, as well, computer scientists, we want to tell computers what to do. That's what our job is. Our job is to leverage technology, whether it's computers or computer-like things, to solve problems in the real world. Now, sometimes that's programming, just straight writing programming, but even that means many different things. That's why I always emphasize this idea that computer science is not computer programming. Rather, computer programming is the tool that we use to solve problems in computer science. But up to this point, when you think about programming, you think about coding, you probably always fall pretty quickly onto things like Python, Java, C#, C++, general purpose programming languages that are meant to solve general purpose kinds of problems. And maybe for the most part, those are the kinds of languages that you do use. But fairly often, if you work in kind of a newer field now, data science, it's a newer popular field. It's been around for a while. Something like that, maybe Python is kind of the go-to move right now for data science. But realistically, what you're using is this general purpose programming language that is Python to solve data science-y type problems. But most of the time, you're using 2 or 3 or 4 data science kind of plugins for Python, and 98% of the code you write is in terms of those plugins. As opposed to you writing a whole lot of, generalistic Python code. So you're leveraging an existing language that you already have some familiarity with, but most of your programs are not going to look like deeply logical Python programs. Instead, it's going to be like load data set, that's one line, and then, display some graph stuff based on 2 or 3 parameters that you have. So you're really just using Python as the intermediary between you and a bunch of tools that are then using your computer's processing power to create, visual graphs and things like that. So one of the things I want us to do in this class is to kind of, I guess 3 things. I want us to broaden our horizons when we think about programming or programming languages. Don't just immediately dive in and think, well, I don't like programming. Well, maybe what you really are saying is, I don't want to sit there all day long writing software applications that ultimately give you an iPhone app that checks the weather. You know, maybe it's that application of computer programming that's not really your cup of tea. Or, you know, I don't want to use computer programming to create websites or something like that because that's too much designy type stuff. You know, or maybe you only like to do back-end stuff and you want to write APIs and things like that. So that programming skill set applies to lots and lots and lots of different things. And one of the things we want to focus on in this class is how are languages actually put together? What are those constructs under the hood in programming languages? Okay, so we mentioned here that a programming language is the bridge between the human and the computer. We can tell a computer what to do. All right, and we go, you know, this, many of you are seniors now, so, you know, how do human beings solve problems? We use our memory. Ay, ay, ay. Nailed it. Ask questions. Still nailed it. Repetition. All right, 100% of programming languages have these facilities. So in here, what we're going to do is we're going to flip the tables and we're going to say, well, what if I had to invent my own programming language, with which I will then use that as a bridge between me and the computer to solve some problems, tell the computer what to do. But I was inventing my own language. I don't like Python. I don't like Java. Maybe it's a syntax thing you don't like. Maybe the kinds of things that you're doing for your job, maybe you're creating a programming language specifically for the kinds of things that you do day in, day out. And maybe you find yourself kind of doing the same 15 or 20 tasks over and over and over and over again. And maybe there's a benefit to you to spend a little bit of time up front kind of creating your own language, your own convenience tool that allows you to then leverage and do your job more easily moving forward because you're always doing the same stuff. And maybe some of that stuff is kind of error prone. And if you automate it and move kind of the human aspects of creating errors out of the equation, maybe your life gets easier, your job gets better, turns into raises, whatever it is. All right. So in here, we want to think about creating programming languages. All right, so creating programming languages is going to ultimately come down to how do we create these facilities to generate a programming language, you know, to provide these tools so that we can solve problems. How do we do that? Well, there's several different ways we can kind of look at this. You know, we've thought about before that computer programming languages come in a couple of flavors, right? We have interpreted versus compiled. What's the difference between an interpreted language and a compiled language? What's the difference between those?
Is it compiled translates before runtime and then interpreted is during runtime?
Yep. So interpreted language, we read high-level code at runtime and then convert to, let's say, low-level code. It might not actually do a conversion. It might just do equivalent logic at the same time. Compiled, read high-level code before runtime, and then turn it into a format that can be executed at runtime. All right, so the traditional model of this is we might think of Python as being an interpreted language, where we write the script, we run it, and it gets interpreted in real time. Or we might think of Java C++ as being compiled languages, where we write the code and then we run it through the compiler and it gives us an executable, which we then run. We kind of saw the middleman there with Java, where the executable was Java bytecode, which then ran in a Java virtual machine. But last semester we saw C++, which ultimately gave us a executable file that we could run, execute. All right, so these are kinds of the different kinds of programming languages we look at. Now, this course specifically, well, let's look at it this way. So let's say interpreters versus compilers. So we talked about what the difference is between the interpreted language and the compiled language. What's the difference between creating an interpreter and creating a compiler? Well, let's talk about compilers first. Creating a compiler involves a lot. Okay, compilers are pretty complex. In fact, and you can almost see this in the evidence. If you look at, the most popular programming languages that are out today, you probably notice that your mainstays, Java, C#, C++, C, those haven't changed in years and years and years. The only new kid to the table in that kind of group of compiled languages is Swift, right? But every 5 minutes, there's a new interpreted language that comes out. You still have your popular ones. Python's very popular. JavaScript's very popular. Go is becoming kind of a language that's growing some popularity. But at the same time, you could probably find 15 or 20 languages that nobody even heard of a year ago that somebody has created since then. Those are all interpreted languages. Because creating interpreters, this goes back to this idea, I don't know if I wrote it down or just said it out loud, but this idea that if you have a job and you need to create an abstraction for, I use the example, if you have a programming job and you have to do kind of the same thing over and over and over again, it might be in your best interest to spend some time, invest some of your time to create an abstraction. Maybe that abstraction happens to be an interpreter that sits between you and your final product so that you can write things one way that's convenient and less error prone. And it ultimately translates it into something that is the output that you used to produce, maybe with in more time or with more errors. So interpreters are significantly easier to write because you can consider them as a layer of abstraction between the human being and the computer rather than something that is translating from zeros to ones. So we might say this: interpreters are much easier. And then the question is, well, we might say that why aren't they all interpreters? Well, more modernly, most new languages that come out are. Why are interpreted? Let's go this route. Pros and cons of interpreted languages. So what's good about interpreted languages and what's bad about interpreted languages?
Are they faster to run?
Well, I don't know. Is that a question or are you answering?
I'm like 90% confident in the answer, so I mean, I would say it's my answer.
You're 90% confident that interpreted languages are faster than compiled languages.
Yeah, because I mean, just thinking about it, if you have to compile something, when you save it all for the end and you have to compile it and then translate it into an executable form, then I would think that they'd be faster. So
what do you mean by faster? Maybe you need to, before I tell you you're wrong, maybe you need to explain what you mean by faster.
I guess at runtime, the code is executed faster, perhaps, is the way I'm trying to phrase it.
Yeah, no, so you're definitely wrong. Try again. They're slower is a con. Well, so I mean, it goes back to your exact logic, right? Your exact logic was, well, because you have to go and before runtime, turn it into something else that can be used right away at runtime, which that happens in compiled languages. Compiled languages would be faster because you don't have to do extra work during runtime. You do have to do some extra work ahead of time, but once you've done it, then you can just use it, right? I guess you could think of it like this: is once you've assembled your bicycle and pumped up the tires, now your bike is convenient to use on a daily basis. You can just go out and use it. But if every single time you want to use your bike, you have to assemble it and you have to pump up the tires and all that stuff, then it's much more difficult. It's much more difficult to use, less convenient to use, something like that. And it'll take you more time to actually hit the road and go somewhere. All right. So putting together your bicycle and pumping up the tires every single time you want to ride is like the interpreted language version of that. Whereas having it already put together and tires pumped up, it's all ready to go, is like the compiled language version of that. So we're going to say a con of interpreted languages, they are slower. But I'll throw a little caveat here. Do we care? Do we care that they're slower? Let's say, generally speaking, the answer is no. So then the question is why don't we care?
Is it because computers are so fast now?
Yeah, computers are fast. So unless we're doing something crazy, something video gamey or, something that's really putting a lot of stress on our computer, we're barely breaking a sweat, right? So just because the language is slower, still that doesn't mean that it's not perfectly acceptable for huge, huge percentages of problem solving. Okay, but we could still call it a con. It's at least something we should consider with interpreted languages. So we might say a pro of interpreted languages is some people might call them easier to learn. I don't like that because I actually don't think they are. I think there's more caveats with interpreted languages than compiled languages. I mean, if you look at Java, C#, C++, and C, and throw Objective-C in there, those languages are so similar to each other that you don't have to make huge leaps to learn one versus the other. It goes pretty quickly. Whereas if you start learning a brand new interpreted language, because they have gotten farther and farther. If you remember back to 200 when we had that kind of the hierarchy of programming languages, and we kind of you had the C programming language, then what came off that was C++, but then you had this web programming stuff over to the side. You had this evolution of languages, but these languages like Java and C# and C++ and C, these have been around for a few minutes now. And you have these interpreted languages coming out every 5 minutes. And there's a point where they do start losing their familiarity with the original language. They start having their own little weird stuff that you can do with them, or nuanced things that you can't directly reach back and say, oh, well, that's like how you do this in Java. They might have a new little feature or something that starts making it a little bit weird. So the idea is, I wouldn't say that they're easier to learn, but we definitely have more options for specialized solutions. I'll use some examples from some of our students. I'm not sure if Noah is doing this yet, but for example, V is working at SkyGen, and she spent most of this summer creating APIs using a language called Node.js. Let's call it a platform called Node.js. It's a framework plus a runtime. But Node.js is let's call it a programming language strongly based on JavaScript, but it's specifically designed for the specialized solution of creating API endpoints, which would be RESTful APIs, so that you can say, oh, I want to get information X, Y, and Z from, tell me person's address whose social security number is X, something like that, or give me phone number for person with first name this and last name this. So she's writing those APIs and she's using a tool that was kind of specifically, built with those kinds of things in mind. Even though it's based on JavaScript, which is a general purpose programming language that you can do all sorts of things with, you would probably pick Node.js if you're doing specific webby endpoint types of things. It might not be your first choice if you were doing data science stuff, for example, because Python has far more packages pre-built for it for data science-y stuff or machine learning stuff, things like that. So I think interpreted languages give us a lot of options for specialized solutions because people have either created new interpreted languages or extended existing interpreted languages through modules to let us solve interesting problems. So it's not always a brand new language. Maybe it's kind of a, you take the 97% that's already right about it, and then you add a layer through a module that makes it 3% different, and you call that your solution. A good example of that is if you've ever done any data science crash course or anything like that, a lot of them use this tool called Anaconda. And Anaconda, when you're looking at it, can kind of look like a, you can think of it like, so anacondas are like giant snakes, right? And a python is a snake. So Anaconda, what it effectively does is it wraps the Python programming language with all of the data science-y extra packages and just makes it all work so that you can sit there and just start writing data science code using the tool that is Anaconda that's really mostly Python, if that makes some sense. So interpreted languages allow us as computer programmers to create customized solutions very, very quickly to things, even though that solution might be slower in the big picture. But as long as that's okay with us because we're running it on a very fast computer or the nature of the work we're doing doesn't have to be that fast, we would call that a good thing. Now, pros and cons of I'll just actually steal this slide, of compiled languages. We'll just actually steal this bottom part here. We'll say faster, but do we care? The answer is maybe. Depends on what we're using it for. So we use some examples of our compiled languages. So let's take Java, C++, C#, Swift, Objective-C. Pretty much covers the cool kids. We'll throw C in there just for posterity's sake. All right, so those are our compiled languages. We haven't seen that list change in a very, very, very long time. As I mentioned before, that's kind of evidence that creating new compiled languages is either difficult or it is not, the juice isn't worth the squeeze is the way I might put it, where maybe it's complex enough that it doesn't give us enough advantages because this idea of it being faster might not necessarily matter for a whole lot of applications. Partly because, as Clancy said, our computers are getting so fast that it's, we don't necessarily care about it anymore because, who cares if we're having to work our CPU extra fast? That's its problem, not ours. And it's still sitting there idle 92% of the time, something like that. But the cons of a compiled language is these are very difficult to create. And the question is why? Let's dive in a little bit. What does a compiler actually do? Okay, so Sarah a little bit ago told us that it kind of converts between a high-level language and a low-level language, right? Okay, but let's take one step deeper into that chasm. What is it actually doing? So we have our C++ program, right? So we'll just leverage what we talked about. Most of you, or many of you, had the 300 class last semester. So we have our C++ program, and we run that through our compiler, right? So we run that through G++, and what's actually happening there? What's coming out the other side? Well, here, I'll skip a step here. We'll say the G++ plus the linker. What's coming out on the other side here?
Binary?
Even before binary. So this would be our assembly code. And then that ultimately gets translated. Well, we'll just say binary after that. By the assembler. So this goes to the assembler, which then executes the binary, or turns it into binary, which runs on the actual CPU. Okay, but all this happens pretty quickly. We don't really need to worry about this as being a major issue. Once we get it down to this level, we're in pretty good shape. But tell me about assembly. What is assembly language? Remember a long time ago, we had a slide that looked something like this: 3 kinds of programming languages. We have binary, so I would probably call it machine language. Machine language, so that's our zeros and our ones. We have a low-level language. And we have a high-level language. What's the difference between low-level and high-level languages?
How easy it is for the human to write it.
I broke up a bunch there.
How easy it is for the human to write it and understand it. The
Okay.
high-level language is more English-like.
Yeah, that's definitely a true statement. Humans would prefer to write high-level than low-level. And why is that? When we talked about this in terms of the CPU. A low-level language operates in what way relative to the CPU and versus a high-level language? This guy was a one-to-one relationship with the CPU. This guy was a one-to-many relationship with the CPU. So what does that mean? What does it mean to have a one-to-one relationship with the CPU?
For every statement you write, it's a direct command versus one line of code really meaning.
Yeah, so we kind of explain the CPU as being this thing that's like a collection of magic tricks, right? And one line of code in a low-level language like assembler, x86 assembler, let's say, translates into exactly one of those magic tricks on the CPU. Whereas one line of code in a high-level language translates into a whole bunch of those magic tricks on the CPU. Okay, so a human being would rather use this power tool. And ultimately, I mean, at the end of the day, the computer is going to operate on this. Computers eat machine language. That's what they need, zeros and ones. One way or another, that's what we're feeding that computer. We're feeding the CPU zeros and ones. So if a human being is doing the talking, we'd rather use this power tool and then have things that sit between us and that CPU that ultimately turn it into machine language. We'd much prefer that than writing at this level, which is possible for a human being to do. We can operate it in a low-level language, where every line we write translates into one of those magic tricks on the CPU. We're not having to write the zeros and ones directly, but we're operating at a pretty granular level relative to the CPU. So if we could help it, we'd prefer to skip this step. All right, so if we kind of expand this out, let's put it in the very next slide. Humans like power tools. We would prefer to use a high-level language. But we understand that ultimately it needs to get converted into machine language. So then we could say that it is easier to convert a low-level language into machine language than it is to convert a high-level language into machine language. Why is that? Well, a low-level language has a one-to-one relationship. So every like here, I'll bring up a do hello world Linux assembly. This is one you've seen before, and we'll review this guy. All right, so this line right here, move this into this. This move command, this is a line, this is one command supported by i86 assembly. This guy has a corresponding number associated with it. This might be magic trick number 14, for example. All right, so converting this guy right here into binary says, well, figure out what magic trick this guy, maybe we have an 8-bit instruction list, which means we can have 256 unique instructions. So we have 8 bits for instruction 14, followed by this guy is a number, he's one of our registers. So this guy is going to be, you know, maybe another 8-bit number, let's say, for a unique value for one of our registers. So now we have 16 bits, so 8 bits followed by 8 bits. And maybe this guy is a memory address, and maybe in this, maybe we support 32-bit memory addresses here. So this is 32 plus 8, which is 40, plus 8, which is 48. So we'll have 48 zeros and ones that are ultimately made up of which instruction number is this, which unique hardware register is this, and then what's the memory address of this guy. All right, so that's how converting this line of low-level code into machine code works. I mean, it sounds kind of complicated, right? But really, it's just a lookup table. I go and look up in my documentation and find out which CPU magic trick the move command is. And that's going to have a binary, an 8-bit binary number associated with it for magic trick, you know, 13, 14, 17, 162, you know, whatever it is. It's going to have a magic trick number associated with it. So, you know, the idea here is that if I go from a low-level language to machine language, that is easier to do than if I go from a high-level language to machine language. So we go back here and, well, if I'm in Java, for example, system.out.println, hello world. All right, that is one line of code in the Java programming language, which is a high-level language. And remember, high-level languages have a one-to-many relationship with the CPU. So this single line of code I'm writing here will translate into many lines of machine code. Now, we just saw how easy it was, relatively speaking, to take one line of low-level code and convert it into its equivalent one line of machine code. Not a big deal, just a convenience for human beings, right? We'd rather write something that looks like this. I want to move this value into this register, and I'm moving it, rather than having to remember the exact sequence of zeros and ones for the move command, the exact sequence of 0 and 1s, which uniquely identifies this hardware register, and having to memorize the memory address associated with this dude. All right, makes sense? It's just a lookup. It's a translation that isn't that big of a deal for a computer program to be written to do that, but it is a convenient thing for us. And we have the proof of this, you know, with our smartphones. Years ago, if you wanted to call your best friend, you had to have their phone number memorized, and you called them. Now you just click their picture, you tell Siri to go ahead and call them, or whatever it is. You know, you might only actually know the actual phone number of a very small percentage of the people you talk to regularly, because you rely on that, on your technology to do the translation. You know, I'm talking to Mike today. I don't care. And actually with like iMessage, you don't know if you're talking to Mike on an SMS with his phone, or if you're talking to him through iMessage. through data. You know, it just does the magic for you. It's doing that translation for you, and it just makes your life easier. But if I write this one line of code, this guy right here, this is one line of high-level code. Ultimately, it needs to get turned into this as an intermediate step, and then ultimately turned into the zeros and ones. So we already decided that the 0 and 1 conversion thing isn't really that big of a deal. Cryptic, a little bit complex for a human being, but it's just a lookup table thing. But turning that one line of code here into all of these low-level codes, I'm telling you, is very complex. The question is why? So let me actually just kick it to another, well, we're seeing it here. So compiler takes high-level code, turns it into turns it into assembly. Oh, I actually already have it written, right? So we take a high-level language, we compile it, we turn it into assembly, it then goes through the assembler, which converts it to its equivalent binary and goes to the CPU. So we care about this guy right here. How difficult is that piece? So I'll ask the question here, what is required for a compiler to work? Okay. Well, we need to know the programming language. That's kind of a given, right? What language? What else do we need to know?
You need to know what kind of CPU it's running on.
Say that again.
Would you need to know what kind of CPU it's running on?
What kind of CPU? Yeah, so you need to know the target architecture is what it's called. So what CPU architecture? What else do I need to know? Now, keeping in mind that what CPU architecture, that says which language am I using here? So Intel processors understand this language. But if it's not an Intel processor, it's a MIPS processor or something like that, which most of you probably haven't heard of or dealt with before. But it's just consider it's different than Intel. You know, it's used for more specialized purposes and things like that. But if it was a MIPS processors don't have lines that look like that. They might have lines that look similar to that. Actually, they do have a move command, but their registers are not called this. They have other names. So the reality is, the punchline is that this is not a legal line of MIPS. That's a legal line of x86 assembly. So we need to know what the target architecture is if we're writing a compiler, so that we can make sure we turn our high-level language in whatever language. So, you know, the language is not that important here, because if we're writing a compiler, we'd be writing like the C++ compiler. Like last semester, we worked with C++ in the 300 class. So the C++ compiler we used was called G++, which was the GNU C++ compiler. And that guy had, you know, he was already assuming the language you were feeding it was C++. But he then needed to know, what am I spitting out? What's the target architecture? Are you going to run this on an Intel-based machine? Are you going to run this on a MIPS-based machine? That's something it needed to know, so it knew which version of the assembly code, or which language of assembly code am I translating this into? What else does it need to know? So let's pause the question for a second. Let's go back and review this assembly. This is something we looked at in 200, so it should be somewhere in your brain maybe. So this is an example of x86 assembly for Hello World for Linux. So what do? These first 4 lines, we are staging some data. We're moving into this hardware register, this memory location, we're moving the number 4. This memory location, we're moving the number 1. This memory location, we're moving the actual message that we want to write. This memory location, we're moving the length of that message. Then right here, we're interrupting our program, calling upon the kernel. That's the actual operating system, in this case, Linux. What does Linux do? The first thing it does is it goes to this register, this memory location that says, what do you want me to do? Ah, you want me to perform magic trick number 4. That's syswrite. Syswrite is a function that requires 3 inputs. I need to know, where am I writing it? What am I writing? And how long is it? All right, make sense? So not only did I need to know, okay, so then we do that. So it does its magic trick there, and it ultimately has the operating system call its syswrite on these pieces of information, and hello world gets spit out to the screen. Then we come back to our program here. We move into EAX, which was the same place we had moved the 4 into before. We moved a 1 there, and this is associated with the Linux system call called sysexit, which gets us out of the program. Okay, now we also moved into EBX as 0, which is the result of our program. Linux pretty commonly has programs return a 0 if everything went fine, and return something other than 0, indicating one of potentially various error codes that might have happened. But anyways, this, if we look at this line here and we look at this line here, both of those guys come right before we ask the operating system to take a peek at what we want to do. So what I'm saying here is actually we're still looking at a power tool. Even though we advertise assembly language, this low-level language, as being a one-to-one relationship with the CPU, we're actually taking shortcuts here because there's other programs being called here. When we call this line right here, this other program that was written as part of the Linux operating system is going to get called, and it's going to peak in these couple of places. When we get down here, this other program that was written as part of the Linux operating system is going to get called, and it's going to peak in these other places. So to get back to our slide, we need the target architecture. We also need the target OS. Why is this? So that we can incorporate the system calls from the OS. Now, most of you had 350 maybe last semester, something like that. What is the job of an OS? What job does the operating system perform? And this goes back to Dr. Locklear's starting point, when most of you had 150 as a starting point. That's now 175 is our new starting point, but his concept of the grand ideas of computer science, how all these things interlink. All these classes, they might feel standalone-ish at the time, but they're all related to each other. So what's the job of an operating system? Why do you use Windows or Mac or Linux? Why do you do that?
Does it manage the resources? Sorry.
Okay, yeah, manages their resources for the computer. What would be the alternative? If we didn't have Windows or Mac or Linux, what would the alternative be? Well, I don't know. I hit the power button on my laptop and one of those 3 pops up. We go back to the old days. I probably showed you this picture at some point. You saw it in 150. Let's look at like UNIVAC. Actually, let's look at EDVAC. Yeah, that's good. Well, maybe, well, whatever. This is close enough. These are all little light bulbs, if you can see on the screen, that you have to turn on. You physically interfaced with the computer. You know, this guy's not using a piece of software, right? He's going on and turning on, they're called vacuum tubes. He's turning on these little light bulb thingies to represent zeros and ones, whether it's on or off. So he's physically interfacing with the computer. And the computers are like the size of gymnasiums, right? For computers that aren't even as powerful as, like, I don't know, some of our socks today. I actually saw that the other day. There's a company that's selling smart socks. That I guess is something to do with foot health and number of steps or something like that. I'm not sure we need smart socks, but cool that we do. We need a smart toaster before we need a smart sock. Otherwise, we're not going to be able to get Yoda on our toast. All right, but before we had our OSs, before we had Windows or Mac or Linux, or even go back to less convenient OSs like DOS, you know, let's say where we didn't have drag and drop, and what's a mouse? Mice don't do anything. Before we had all those things, we had to physically interface with our computers, which was not convenient. And you imagine that probably slowed us way down and also drastically limited us on the types of things we can do with our computers. Fair enough? Okay, so that's what happened before that. So when we say, what's the job of an OS? This guy takes our desires and turns them into system calls so that we don't have to figure out how to directly manipulate the hardware. You're not popping open your laptop and getting the soldering iron out and hoping you touch it in the right places. That's just not how computers work today. But back then, this is how it worked. All right? So our compiler, this is a really complex thing. We got to say, here's the language I want you to convert from. This is the architecture I want you to convert to. And oh, by the way, this program is going to be running on this particular operating system, which already has some power tools written, which you can now take advantage of to solve some of your problems. There's several variables in there that that go from you writing a line of code that looks like this and turning it into something that looks like, oh, I already left my, but we have the technology. That looks like this. That's why you have not seen newer compiled languages come out more recently, because the languages we have are already very powerful. And it's not that compiled languages are not useful. We do need them sometimes, as Clancy pointed out, when we need something to be really, really, really fast, and it actually needs to be faster than what our extra fast computers can just pump out. We need to have nothing standing in the way, all right? But when we're talking about normal, making our lives easier as language theory folks, saying, okay, well, I really want my syntax to look like this, or wouldn't it be cool if you had a version of a for loop that, you know, allowed you to say a little bit more, because when I write my for loops for my job, you know, 99 out of 100 times, I'm doing these 5 things. So why not incorporate that into the syntax of that for loop so that I don't have to write 3 or 4 extra lines for the rest of my career in that place? Something along those lines is where we start getting into interpreted stuff. All right. So the idea is that in grad school, so in our grad program, we have a compilers class specifically, where we do look at this process of how do we go from a high-level language to ultimately machine language, to a low-level language, taking into consideration the architecture and the target OS. But at the end of that semester, after a whole lot of code and stuff we're writing in high-level languages, usually C, because we ultimately need to get it written, we need to convert it into zeros and ones ourselves. Because then otherwise you have a chicken or the egg problem, right? You know, like I need a compiler to write a compiler, but who wrote the original compiler? So the original compiler was actually written in assembly language, which was then assembled into binary. So it's kind of a, you know, it's a complex task. So it's a neat class because you're getting really down to the nitty gritty, but you really gain an appreciation for just how complex compilers are as part of that, because what you have in the end is something that's not necessarily overly functional. You know, we might have a compiler at the end of a semester that can take your one line of high level code, actually probably can do a little bit more than this, but just as an example, maybe by midterm, you have a compiler that takes your one line of high level code and turns it into this. And that's not nearly as impressive as having a whole programming language that, you know, implements recursion and loops and functions and variable environments and all sorts of things like that. We have a lot more flexibility with interpreters, and it allows us, from a language theory perspective, which is what this class is all about, it allows us to explore. So let's get a slide on what is language theory. This allows us to explore the ideas behind each of our, let's call it, common programming tools. So we can say things like variable environments, you know, i.e., how do we do memory? We can say conditionals. That's our asking questions. We can say repetition. That's our loops and our functions. We can keep adding to this. We can say, what about recursion? If we wanted to implement recursion, what would that look like? Something you maybe remember from the 300 class, we dealt with stacks. And I would have said something along the lines of, all recursive programs can be written iteratively with a stack. So now we start seeing how some of our data structures play into the implementation of our programming languages, which then use those data structures to solve problems. So it allows us to not get too deep into converting this one line into a bunch of zeros and ones, but instead of staying kind of at the high level, but thinking about how do I write high level code that mimics a for loop, that mimics a function, that mimics a variable environment. So you're forced into going down that path of thinking how our language is put together. What do those constructs look like? As opposed to going back to this level and saying, which language am I really designing here? Am I designing an interpreted language versus a compiled language? If you're going to go the compiled language route, that's fine, but you want to have a good reason for it. And maybe something that says, well, what's wrong with the current languages? We certainly have very few special purpose compiled languages today. Way back when computers were much simpler, we didn't have interpreted languages. So even the special purpose stuff were compiled languages. Now you do have a lot of embedded systems working off of C, but what you have is you have a very simplified compiler, so you can't use all of the C language. You're using just a, you know, little tiny nook of the C language that's allowed to be used for, you know, writing a program for like a dishwasher or something like that, which is like an example of embedded systems. Okay, so kind of, let's say that's kind of our overview-y stuff of what is language theory and why are we going down this interpreted path. It allows us to focus on the language constructs rather than the bits. Okay, so any questions up to this point? All right, so let's talk about tools. So a tool you're going to need for in here is something called Dr. Racket. Used to be called Dr. Scheme. I think I have a link to it on the Blackboard page. So it's racket-lang.org. So download this guy. So this is an interpreter for a programming language called Scheme that we're going to be using. All right, so I have 7.5 is my version of Dr. Racket. Oh, I got to get the whole. So on a Windows machine, there's probably an installer, or it might just be an icon you just drop. On a Mac, you just drop the whole folder in here. And the current version is Racket 7.8, but that won't make any difference. I just want to make sure I'm using my version is 7.5 on my computer. So I just want to make sure I'm running the same version as you're running in case there's any weird things. Here, I'll just let that keep cooking while I keep going on. So we're going to be using a language called Scheme. Now, way back in 200, we probably had a slide that said something like, there's 3 different kinds of programming languages. There are procedural languages, there are object-oriented languages, and then there's functional languages. And I kind of said, oh, don't worry about functional languages right now. We're really focused on the difference between procedural and object-oriented languages. And if you remember my example, what was it? The procedural telephone versus the object-oriented telephone. Procedural telephone looks like the big pile of wires where all the public interfaces as well as the details you never need to touch are just laying out there. Where the object-oriented telephone looks like a telephone. You know those wires are stuffed inside of it somewhere, but you don't have to interface with them very, very often. Okay? All right, it sounds like Racket got... All right, here's my Dr. Racket 7.8. I'll just drag it down here so I... All right, first thing you want to do when you first open the thing is you want to go up here to language. You want to choose language, and you want to choose it, probably advanced student is what it used to be called, yeah, advanced student. So if advanced student isn't already selected, choose advanced student. It'll make your life easier. And your examples will look the same as mine. Okay. So,
Sorry, could you just could you repeat that last step quick?
Nope.
Sad life.
So you go to language, choose language. Because Dr. Racket is actually a tool. It used to be called Dr. Scheme. It's actually married to that book, the Essentials of Programming Languages book. So they actually have some different versions of the language in here for depending on the difficulty of kind of how deep you're getting into it. And we're going to use the advanced student one. All right, so Scheme is a functional programming language. It is list-based, which most functional languages are, as opposed to, if you remember, I usually call Java is a string-based language. And that's not fair to say that all high-level object-oriented languages are, but Java in particular makes strings very convenient to work with. But as far as Java is a string-based language, Scheme is a list-based language. So we work with lists heavily in Scheme. We can also say Scheme is a very, very small language. Okay. Now, in more recent versions of Scheme, they've actually added an ability that we're not going to be allowed to use in here. So Scheme does not support loops. Technically it does now, but you're not allowed to use them. If you want your programming language to have loops, you have to write it yourself. So we will be accomplishing this through recursion. So in the past, when you deal with recursion, when you have a function that calls itself from within itself, and remember how kind of difficult that is for us, you're going to be very good at recursion by the end of this class. Okay, but the real thing here is the reason I choose scheme here. We make this argument back here that, okay, well, we're choosing, we're going the language theory route here where we're looking at an interpreter. We don't want to get too deep into the weeds because our real focus here is how do typical programming constructs work? That's our actual focus in this class. Well, what we don't want to do is we don't want to have a language that does too much for us or that has too many power tools built into it that makes things too easy. So we pick a language like Scheme that then allows us to almost have one hand tied behind our back. It's a pretty small language. So we're going to go ahead and start off confusing you today. So we'll start off with lists. So a list is an opening, closing parenthesis. This guy here is the empty list. That's the list with nothing in it, kind of like the empty string. This is a to list containing the numbers 1 and 2. This is a 3 list What's this one? Still a 3 list. This list contains 3 elements. Element 1, element 2, which is a list, and element 3, which is a 4. All right, so lists work this way. This is what they look like. And lists are collections of scheme data types. So we'll call this a collection of 0 or more scheme data types. And for us, that's going to be numbers, booleans, symbols, and other lists. And we'll get to that as we get deeper into it. All right. That's what a list is. Working with lists. Well, we have to construct, we have cons, which constructs a list. We have car, which returns the first element in the list. We have cdr, which returns everything except the first element as a list. We have list. Actually, I'm gonna, well, I'll introduce it, which also constructs a list. We have append, which combines 2 lists together into a single list. All right, so now we go back to programming languages. So we're going to say we have memory, which is accomplished through a define statement in Scheme. We have conditionals, which is done through the if in Scheme, and we'll get to that. And then we have repetition, which is done through, we're going to say recursion and lambda expressions. And we'll get to that soon. But right now, we're going to mess around with lists some. So I'm going to go over here to Dr. Scheme. And I'm going to go ahead and define a couple things. I'll define list 1 to be the list 1, 2, 3. So if I go ahead and run this program, we see we have no output. But if I just type in list 1 here, it shows me there's my list 1, 2, 3. Okay. So now I already have a variable. And so this is kind of like an interactive terminal. So you can use this similar to how Python's interactive terminal works. But if you want to have your code up top, you can do that up here. So I have my list, and I'm going to go ahead and I'm going to say, give me the car of list 1. And we saw here that the car of a list should be the first element in that list, right? What is the first element in list 1?
1.
Should be a 1. So there's a 1. Coulter gives me the rest of the list as a list. So if I say, give me the coulter of list 1, what should that give me?
List 2, 3.
The list 2, 3. So there's my 1, and there's my list 2, 3. All right, so I can say, give me the coulter of the coulter of list 1. So that strings functions together, right? So the coulter of list 1 is the list 2, 3. What's the coulter of the list 2, 3?
3.
The list 3. Oh, I ran it again instead of typed it in. So the coulter of list, the coulter of the coulter of list 1 is going to give me the list containing 3. So there's my list containing 3. If I take the car of the list containing 3, I'll get the 3. There's my 3. I can also say, give me the car of the coulter of list 1, the coulter, and that also gives me a 3. So we also have shorthand for these, although you never have to use the shorthand. There is a limit to the number of cars and coulters you can kind of squeeze together in this shorthand, but these two lines right here are equivalent to each other. So it's the car of the coulter of list 1. So it makes it a little shorter, but to be honest, for a while, I would stick with this. It'll be easier for you to read, but what'll end up happening is pretty quickly, you're going to be having nightmares about parentheses, because you'll see we have a lot of parentheses in here. All right, and then we can also construct lists. So I can use cons. So I can cons a 1 onto the cons of a 2, onto the cons of a 3, onto the empty list. So the second parameter of a cons always has to be a list. So this is consing a 3 onto the empty list, which will give me the list containing 3. I'm then consing a 2 onto the list containing 3, which will give me the list containing 2, 3. I'm then consing 1 onto the list containing 2, 3, which will give me the list containing 1, 2, 3. So there's my list 1, 2, 3. I can also accomplish that by saying list 1, 2, 3, and I get the list 1, 2, 3. Now, what if I say cons 0 onto the list 1, 2, 3? I get the list 0, 1, 2, 3. What if I say cons the list of 1, 2 onto the list of 2, or let's say 3, 4. I get the list containing the first element is the list 1, 2. The rest of it is the list that I provided it for cons. So this constructs a list by putting this element as the first element of a new list that expands this list. As opposed to append, which melds two lists together. So this one gave me, when I used cons, I constructed a list whose new first element was this guy. And it got added on to the list 3, 4. So that gave me the list containing list 1, 2, followed by 3 and 4. When I used append, giving it two lists, it gave me a single list with the contents of those two lists. Make some sense? Okay, so let's see. To find the textbook. So I'll give you fair warning, first of all, is in this textbook, it's going to read like stereo instructions for a while. I promise you it'll be intimidating at first, but then it'll actually get easier once you get into it. All right, so what we're going to look at initially is this idea of inductive sets of data, ways of describing languages. Now, up to this point, when we think about languages, we pretty much always think about programming languages, right? But for instance, what is the language of the decimal number system? Well, what's the language of that system? First of all, what's the alphabet that makes up, what are the symbols that are legal symbols in decimal numbers?
0 to 9.
0 to 9. All right, so all the numbers that we write that are decimal numbers are made up of zeros, ones, twos, threes, 4, 5, 6, 7, 8, 9. Okay, but sometimes our numbers have more than one of those, right? So you have to have at least one of these numbers. So I can have a single 0 through 9, followed by another 0 through 9. And actually, usually we don't allow our numbers to start with zeros, right? So we have a 1 through 9, followed by a 0 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 through 9, so on and so forth. But what's the longest number you can write?
As long as you want.
Very, very talkative class today, right? Yeah, infinity. We can just keep writing numbers. So how do I describe the language that is the decimal number system? Well, so the first chapter is going to look at some different ways of describing these languages. Ultimately, we're going to come down to a something called a grammar that has a list of productions that says what a grammar is. So we can really say that we have the language of decimal numbers. So this tells us how can we create a legal decimal number. It's going to be a 1 through 9, because we can't have a decimal number that's nothing, right? That doesn't exist. It's no, we can't say there's nothing here and that's not called the empty decimal number. All decimal numbers will start with a 1 through 9, followed by potentially some more digits, right? So we'll have 1 through 9 followed by 0 or more, 0 through 9s. So this is one way of representing the grammar of the decimal number system. That is a language. And we can create things that match that language. Where can I get there quick through the clicky? Nope. All right, so I mentioned that we're going to be doing a lot with recursion in here. So we're going to be dealing with recursively specified data. And this is kind of an example of it already, where we say, you know, this is kind of, we had to give up because we said the rule was that the very first digit can't be a 0. So we said, okay, what's this followed by any more of the same thing? Basically the same thing. So that's kind of like a function calling itself from within itself. So we're saying it's this followed by 0 or more of those. All right, so they go through initially telling us about like what the language of natural numbers is, giving you some examples of this stuff. This is mostly going to be stereo instructions. So I'm going to hit you with the highlights of this on Thursday, but pretty quickly we're going to get into grammar. So this kind of gives you a starting point for grammars, but here's like an example of grammars for production. So we can have something called a list of integers. A list of integers can be an empty list, or it can be a list containing an integer followed by another list of integers. All right, so we can describe languages this way, and then we can write code that allows us to do stuff with things that are members of that language. All right, so homework for Thursday is to get your hands onto the textbook. But like I said, definitely don't use the PDF that's floating around. That is exactly what I have open here. You should buy the book and pay real money for it. Okay, so I will see everybody on, we're done at 2:35, right?
2:25 actually.
Why didn't somebody tell me to shut up?
Because we respect you too much.
And
we don't want to get told to shut up in return. So
I really thought it was 2:25. What time did we start?
1:10.
Yeah, 1:10 to 2:25. All right, yeah, sorry about that. Tell me to shut up next time. Okay, so one way or another, get the book for Thursday, and we will pick up from where we left off here, and we should get into some scheme stuff, I think, on Thursday. But make sure you got Dr. Racket and play around with some of that list stuff. I think you'll find it intimidatingly mind-shattering.
Just a quick question. So I think Locklear students got an email saying that it seems like they want you to go to class. Like they say they don't want kids attending all online this semester is what it seems like. Sure. But I don't know. It's weird because I'm hearing mixed things. Some teachers say you're okay with it. I don't know. I just want to know if you had heard anything about that.
Yeah, I mean, I think the general thing is that the university, I mean, okay, this is my opinion. My opinion is that, you know, the clients for, you know, Concordia generally want a face-to-face education. So faculty are supposed to be doing everything we can to make sure that students can meet face-to-face. Now in small classes like this, that's easy. But in larger classes, like my 200 and 250 class, both have almost 40 students in them, it's not practical. So I have options. My option can be, well, I can split the class into 2 halves and then have half A show up on Tuesdays and half B show up on Thursdays and have the other half be online. Or what I'm doing is I'm saying, any of my students can attend my class online or they can attend it in person. I'm doing the same thing either way. It's up to them. You know, I probably the official line from the university is that they want students attending class in person. I would say that I want all students that really want to attend class in person to be able to attend class in person. And students who don't really care to be able to be at, you know, stay home if, you know, weather or it's more convenient for commuting, or, you know, they don't want to put themselves at additional risk if they have concerns about the on-campus environment, whatever it is. So basically I'm making it easy in my classes, but realistically, if your question is what is the university's official policy, it's probably that they want you in class, but it's also an acknowledgement that many of your classes, there's going to be at least half the time probably where you can't be in class because the other half of your class is meeting.
All right, that makes sense. Thank you.
Something like that.
All right, I'll see you on Thursday.
All right.
Yeah.
There are some other scheme tools. I mean, you can use any of them that exist, but you really should probably use Dr. Racket because it's closely linked to the book. So,
Okay.
yeah, I mean, just because you don't like the user interface, I mean, just get used to it.
All right. Okay, I will. All right.
Sound
Okay.
good?